Right, so good morning, everyone. Good morning, and hope you're all up, active, enjoying yourselves, and of course, suitably motivated for the end of the term before the Easter break. Don't wish to be the bearer of bad tidings, but week 17. On the Thursday of week 17, you will have your Physics 2 test. Your Physics 2 test will be on circular motion and simple harmonic motion. I am going to give you one lesson before the test itself, and we will do that, but I'm giving you now fair warning so that you have sufficient time over the Easter break to continue your studies, those of you that are looking at doing additional work. As I have said to you, the questions themselves will be very similar to anything you've had in the booklet. So if you've covered the booklet questions, you've been through the presentations and answered the questions in the presentations, then you're going to have no problem with the test. The standard format is going to be 10 multiple choice questions, and then a choice of, I think it's one of three or two of three. I can't remember. I don't have the paper in front of me. But I will go through it all with you. I'm not, of course, going to give you the questions, but I'm going to help you as best I can so that you do have as much material as is necessary. Now, in all of these things, it is going to be a classroom test. So you will do it in the physics room during the physics lesson. And that will be your test for this year. I am going to, as I say, answer any questions as you ask them. But for today, we are going to continue in the astrophysics. We're completing now the section of the course, which is going to allow us to finish the life cycles of stars, because we'll go through the ultimate demise and the end of all of the different aspects that we are looking at. And that will allow us to then have a conclusion to the section on astrophysics and star formation. The only thing that we need to do after that is going to be to look at cosmology. But what I also said, and you'll see the reason again for that during today's presentation, is to go through the quark model. Now that is going to give us an opportunity to look at the last section of what I called quantum physics. And that will allow us then to see some of the explanations for some of the parts that I have covered in this presentation and will cover in future presentations as well. So just admitting hopefully the last couple of people. So again, just for those of you that have just come in, your test is week 17 during this Thursday lesson. So please be prepared. I can answer questions at the end.
Which date is that?
Week 17. I haven't got my sheet of paper here. All I can tell you is week 17 is the week that you are back in school. So that is the reason we've chosen that particular week. Okay. Now, what I want to continue with today is for you to look at the presentation that I have up on screen. And I'm going to go through, as I've said to you, the final throws. So looking at the final part of the star life cycles, and then look at some of the end results which we hadn't previously considered. Roman says 29th of April. Thank you. Okay, so going to the presentation. We've talked already about the Hertzsprung-Russell diagram. We've seen where the elements are that we need to be aware of. I've talked with you about stellar classes. So the class of stars, very hot stars tend to be class O stars. Cool red stars tend to be class M. The the sun sits somewhere between the G and K type stars. So we have a classification which allows us to identify most of the types of stars we see. We see the colors, so we can guesstimate their temperature. Now, on the corresponding scale, we use the magnitude, the absolute magnitude of those stars that we can view. And there is one major line that exists on that Hertzsprung-Russell diagram. We have on that line the sun as we see it today, as it's sitting in its present state, 4.5 to 5 billion years into its life cycle, and it's now merrily burning away at a constant rate at a temperature of around 6,000 Kelvin. So the surface temperature is conducive to nuclear processes. So there is nuclear burning of hydrogen to hydrogen, potentially some hydrogen to helium, and then helium and heavier elements also potentially being formed. What do we call this region? What's this called on the Hertzsprung-Russell diagram? Try and see that you're awake. That's why I'm asking the question to everyone. It's called the what on the Hertzsprung-Russell diagram? We've covered it before. The main sequence. Thank you. It's the main sequence. The stars fit onto the main sequence. So this is the region we are talking about. Now, we describe these stars as logically Jacob, did he manage to get in? I got a request and then it disappeared. So, Jacob, are you there? No. If anybody's in contact with Jacob, his request came up and then disappeared. So if he comes in again, I will just accept his request. But why we need to do that, I'm not sure. So we've seen the stars. The hottest stars tend to be the brightest. It's sort of logical. If we have a star that is burning brightly, chances are it's a hot star. So it's a blue-colored star. The opposite extreme, the cooler, less brightly burning stars tend to be the red stars. So you'll see them down here, the class represented by the color of these stars on the main sequence. That is the majority of stars that we are observing today. But we can continue to another group of stars that sit slightly off the main sequence. Let me just turn on the laser pointer. So we've got this group of stars just here, which are called the giant stars. And you'll see that most of them have a color similar to the stars underneath them. So we know their temperatures are much lower, and we see that they've moved higher. So they are actually burning more brightly than their other counterparts that are on the main sequence. But why can we see these stars? Why are these stars moved up in the luminosity? Why have we got a star that's gone from the main sequence where it's yellow onto the giant stage where it's now still yellow, but it's moved up in luminosity? Why? Let's have some answers. Per.
Yes. So the thing, from what I understood, is that the color is so dependent on, or not solely, but color is also dependent on the chemical composition of the stars. So if you have giants, they would quantitatively have more light compared to smaller stars, obviously.
But why? Why? Charlie, you've raised your hand.
I mean, intuitively, it's just because they're bigger, I think.
You are correct, but you're also correct, Per, in your discussion. What you were missing was the scientific explanation. They have a larger surface area, and their surface area is emitting more radiation. So
that's what I meant by saying that they have more.
No, I realize that, Per. Yeah. I'm just trying to help you. It's the scientific way we describe these things that becomes important.
Yeah.
Okay?
Yes.
So the size of these now determines their position. So any red star that was burning on the main sequence could potentially achieve the end of its life cycle. We'll look at this again in much more detail in a couple of minutes, and find itself in the giant phase. So they've moved up into the giants. Now, there are also some stars that will fit even further. And these stars, again, are what are called the supergiant stars. And the supergiants, similar to the giant stars, they are just much, much bigger. And these stars tend to move from higher luminosity across the chart. They will maintain their luminosity, but they lower their temperature because they've gone from a certain size of star to 1,000 times bigger, but at a lower temperature than they were previously. We'll see again why that happens in a few moments. We talked about a few other groups of stars which fitted into other regions. Again, a sort of death cycle said a star starts red, moves main sequence, moves up to the giants, and then drops down here to what we call the white dwarf phase. So we find the white dwarfs, which are the areas where the stars are much hotter, but they are much, much smaller. So hence they've gone from giants to dwarfs. So they're much smaller than their original size, which means these stars now reduce their visibility. Their magnitude goes down as well. Oops. So I'll just go back. So to finish that, we've got now all of the positions that we need to have within the Hertzsprung-Russell diagram. Now, we asked a couple of questions last week. There's, for example, some fairly obvious stars that are missing, or say stars, ends that are missing, neutron stars and black holes. Well, black holes, very simple reason why we don't see them. They are black and they are not visible. So we have no magnitude for a black hole. The neutron stars, we will see these are part of the death process of white dwarf stars. So these will be the type of ending depending on the initial size of the stars in this sort of burning region on the main sequence. Oops. Now, moving on, we can see that our stars fit into a number of categories. So we have 4 categories of stars that we have discussed. Each of them has a very significant area on the graph. So the main sequence is where we find most of the stars that we look at fit into this region, which means majority of the stars in the sky are between about 1/10 of a solar mass up to around 30 times the solar mass. Giant stars are the sort of end sequence of those types of stars, where they have then a size or equivalence of around 10 to 100 times that of the sun. The supergiants, firstly, are very rare. So relative to the rest of the graph, we don't find very many supergiants because these stars are about 1,000 times the mass of the sun. So they are about 1,000 solar masses, which is pretty large. The last part on there is the white dwarfs. So these now are the much smaller stars, but burning much hotter than the sun. Now, I showed you a graphic of the OBAFGKM, the classification of stars. Well, this is the classification in the opposite direction, because this starts off at class M, the red coolest stars, and shows the relative size of each of these stars as a perception of their size for main sequence stars. These are not stars that have finished their nuclear burning, but these are stars that are still on the nuclear burning process. So these are the relative sizes for main sequence stars. And as you can see on this illustration, the O class, the blue stars, the ones that on the Hertzsprung-Russell diagram are the far left side, are by far the largest stars, as opposed to the class M stars, the smallest down here, which are on the far right of the Hertzsprung-Russell diagram. Now, all representation is useful for us, but there are some significant differences between these representations. And one of the things that I would like to go through now is just to see how this process occurs in relation to the main sequence. Now, we talked about how stars form. So small life cycle, what happens? I'm not going through the processes that take place, but just want to show this process on the Hertzsprung-Russell diagram. So we start off with our nebula, moving into the protostar, which becomes a pretty large object, which then starts to gravitationally collapse as it moves on towards the main sequence. So the star starts burning, starts warming up, and eventually finds itself on the main sequence. So what we've now got is a star that's gone from a protostar. If this process didn't actually take place and the star sort of just fizzled out, we would then get the formation of a brown dwarf. So the non-star never went into burning, but sort of fizzled out in this area and disappeared. We don't see many of those because it is theoretically possible, but if there was enough gas that started, we do get the formation of a star. So we've now got the star on the main sequence. What then happens is the star reaches equilibrium. It's now in a state of constant luminosity. We say it's constant, but it is actually going to change over time. And the magnitude of that depends on the size of the star. But what we see is that the sun has moved from a sort of orange color to the yellow color, and it's about halfway through its 10 billion year life cycle. The largest stars, these up on the top of the main sequence, probably are only going to be around for tens of millions of years as opposed to billions. But we're looking now at our stars that are moving through the main sequence. And as the star progresses through the main sequence, it will gradually warm up. And we've talked, I think, already about the catastrophe. The sun will at some point come to the end of its lifetime and it will go red, it will expand massively, but during that time building up to that, it will gradually warm. Some would say it's even started doing that now, but we think that the effects that we're seeing are not from the sun, but from the Earth's inability to sustain the life as we have it. But in about 2 billion years, the Earth will become too hot to sustain life. So there will be a point that's arrived at where the Earth's temperature is going to significantly increase and life will no longer be able to live. But I think it's safe to say it's a little beyond our lifetime. As we continue through this cycle, we ultimately get to the end of the burning phase. So the core of the star has been converted into helium. The star collapses on itself and the outer layers of the star expand. So this is now the movement into the red giant phase. So we're now looking at where the stars start to move into this new phase where they get warmer, they get larger, they get more luminous, but their temperature on the outside has now moved them into the red region, so they've changed their character. The temperature of the helium core increases as it collapses, which causes more fusion, and heats the core even further. So we're now getting to the point where the temperatures are getting pretty unbearable. Heavy nuclei, beryllium, carbon, oxygen are being formed, and the star increases in its size. The sun would expect to achieve this phase in around 4.5 to 5 billion years' time. And it will achieve an orb or size which is going to be something equal to or just above the Earth's orbit. So again, if we've not been heated out of our planet after another 2 billion years, by the time the sun achieves this level of red giant, it will have swallowed up the Earth anyway as part of the expansion process. So hopefully we'll have discovered techniques for us to travel to other worlds to find life elsewhere. Now, the red giant phase lasts for a period about 1/5 of the main sequence. So we're sort of looking at a phase now that is significantly smaller in the red giant phase. But the red giant phase is only the end of the burning phase. So when the nuclear fusion in the core ceases, the star cools down and its core contracts. Of course, when it contracts, it increases again in temperature, but this causes the outer layers of the star to be thrown away. So you see these things that we call planetary nebula. And an example is given in this diagram here, where you see the star at the center, and the outer regions here are the regions showing probably different energies here. These are the most energetic, X-rays probably, and the other areas here being thrown off and expanding away from this planetary nebula. Now, the star at the center has gone through a very different process. It has now collapsed, and the release of this energy means that the star will collapse into a very, very dense object, and it will stay in its final phases, not physically moving in the sky, but physically changing in size. And so we'll see now the end of this thing as it now becomes stable and becomes a white dwarf star. This cooling process, and any of you that may have looked at some of the life cycle of the universe may have seen these, this will take several billion years. So the overall life cycle now becomes very significant. So the life cycle of a star like our sun goes through its birth phase, its gradual warming, its formation of the red giant, and then the demise to the planetary nebula and the white dwarf, which is slowly going to cool down. And you can see that this total phase, and we are looking at about 10 billion years as the lifetime of a burning sun. It will take another 4 to 5 billion years for this star to go through its death throes and actually move from a white dwarf into the black dwarf phase. That will be something which is beyond the age of the universe as we know it so far. So we are not looking at an awful lot of these stars that you will be able to see in this phase of their life cycle. Now, I talked a few minutes ago the sun. The sun is a small star in relation to others. Oh, just put these in. You'll see this now, the process as the sun moves from nebula, protostar, main sequence, red giant, planetary nebula, and finally into the white dwarf phase. Now, there is another type of star that's significantly different, and those are the red supergiants. And the red supergiants come from stars that are about 4 times the size of our sun. So not significantly greater, but certainly larger than our sun. And the core again burns through its nuclear processes, producing a structure which looks more like onion rings. So at the center, the hottest part here, we have the fusion of atoms to form iron, silicon, oxygen, neon, carbon, helium, and so on. So we get these formations in rings where the temperatures and stability of these types of atoms are formed within the dying star. And the supergiant, Betelgeuse, which I've talked to you about many times, it's a significant star. If we look at that star, we can see evidence of this burning in the higher frequency ranges. So looking at the ultraviolet, presumably X-ray, would demonstrate something as well. But we're seeing a region of higher intensity. Just one moment. Could you please, could you keep your, hey, I'm talking to you. Keep your voice down, please. I'm teaching you here. So we get to the sequence in our formation where supergiant stars like Betelgeuse are going to go through a different process to our sun's process. And that is the catastrophic end of what we call the supernova. And a supernova is going to be a final death call of a major star. When the iron core of a supergiant is about 1.4 solar masses, this is a possibility. You'll notice that we say here the iron content, not the mass of the star is 1.4 solar masses, but the iron content of the core is around 1.4 solar masses. These numbers all come about through various different calculations that have been carried out primarily by an Indian astrophysicist called Chandrasekhar, who did a lot of the thermal and processes and the mathematics behind the processes in the burning of stars. And that's where these values of particular numbers for particular types of stars come from. So it's very significant. It's the iron content, not the mass overall of the star, that causes the supernova. So in this case, the gravitational forces of this heavy part of the star are too great for the repulsive forces of the electrons. And we get a decay process. And this decay, which you may have looked at last year, means that we can take a proton, and I'm going to talk with you, probably the first lesson after the Easter break. I'm going to go through the quark model with you, because the quark model makes it very easy to understand this decay process from a proton to a neutron. A proton is made up of 3 quarks, and 2 of those quarks are similar in nature. So if we can change the nature of one of those quarks, we can change a proton into a neutron. And that's what happens. Now, the electron is what type of particle? It is significant in this that the electron is a special type of particle. What is that? Electrons are... Somebody? What type of particle is an electron as opposed to a proton or a neutron?
A charged.
Yes, it is charged, but that's not its nature. Its nature is what type of particle? A something particle. Anything?
Subatomic.
It is. It's a fundamental particle. The electron is fundamental. It cannot be broken into smaller pieces. Protons can. Protons are broken into other particles. As you can see here, protons decay to neutrons, giving off huge amounts of energy. So we have a process taking place here which results in the formation of neutrons. So we now find that the star collapses and the core of that star contains nuclei that have a density of about 10 to the power 17 kilograms per cubic meter. I'm going to ask you a question in a few moments where you can calculate something to do with that nuclear density. Now the core becomes rigid. It becomes a solid object, a neutron-based object. And that means that the star is going to be a result of what we call a cataclysmic explosion. The star again shows these outer regions which are expanding from somewhere at the center, but at the center of this particular supernova, we see something different. And these will give us typically an event that will occur when the ion contents fuse and combine, that we produce a luminous star that's about magnitude -15 to -20. That is going to be as bright as sunlight, as moonlight in the daytime sky. So you will see these events if they occur, if they're close enough to us, but they are by their nature going to occur at very distant locations. The Crab Nebula, the remnant of a supernova observed in 1054, is now 1,000 years since the event occurred. We can still see it, we can measure the size here, so we can work out the size of the event that occurred around this. Remember, this is a 3-dimensional, not just a single explosion in one direction, but an explosion in all directions. Now, we use the type of supernova in various different ways. And you'll see here there are 2 types of supernova, class 1 and class 2. Basically, their difference is when we look at these supernova and look at the emissions from them, Class 1 supernova have no hydrogen. Class 2 have strong hydrogen lines. So we are seeing the demise of a star during an event where there is no hydrogen present, which for class 1 supernova says this star has finished burning all of its hydrogen. There is no hydrogen left. So we see no evidence of hydrogen in a class 1 supernova. Class 2 demonstrates strong hydrogen or helium, which means again it's a supergiant that has collapsed because there are still remnants of hydrogen and helium in this object. Why is that significant? It is significant because we can use supernova as what we call standard candles. In other words, it's like having a candle in the sky where we're using that supernova event to actually tell us how far away the event occurred. We know that a type 1 supernova has a known peak luminosity. It tells us that if we know this supernova occurred at this time and its luminosity was measured as however we measured it, we can compare that to a standard star, which we know has a given magnitude of 19.3. All of these supernova have an absolute magnitude which we can observe. Why do we know this? Well, we know the type of star, we know the processes that are occurring, we know the magnitude of the star that will produce ultimately that event. So if we now observe their apparent magnitude, you can determine the distance because we have the formula, the difference in the magnitudes between apparent and absolute gives us 5 times log the distance in parsecs divided by 10. So this formula we came across earlier, but it allows us to calculate the distance to a particular star. Now, there is a calculation in the questions. If you want to have a look at that, you simply need to use the calculation using this formula for the apparent and absolute magnitudes, and it will give you a distance to some of our closest events. We're going to look, though, at one of the results of this, and the result is very significant because we form a neutron star as the remnant of a supernova. And the gravitational forces cause this process of neutron production, which ultimately leads to this super dense star being formed. So what we now have is a star which is super dense. The star is spinning, and because the star is spinning, this is going to display for us the processes where this energy is being emitted from the side of the neutron star. So if the star is rotating about this central axis, energy is being given off in the form of neutrinos, electron neutrinos, for example. These neutrinos are rotating, moving negative charge gives us a wave. That wave is observable in the radio part of the spectrum. So these objects, rotating neutron stars, were first detected in 1967. Now, I started my degree work in 1972, 73, that sort of time period. And one of my tutors was a lady called Jocelyn Bell. And Jocelyn Bell was the lady that discovered pulsars. She worked at the University of Cambridge and was working on a very, very unknown branch called radio astronomy. And radio astronomy at that time was very much, if you've heard the expression, Heath Robinson. It was very much belt and braces. So we fastened things on wooden stands. And the apparatus that Jocelyn Bell used looked like a fence at the end of a farmer's field, because it was magnetic field attracting, so it was like netting on a fence, and it was supported by wooden stakes. So this object that looked, it was pretty big, so it was probably about 700 or 800 meters long, electrically connected. So it had a lot of things that made it a scientific piece of equipment. But in that equipment, they detected a radio signal that was rotating about this axis just here around 30 times per second. And that was the first event that was recorded as what we called a pulsar. And pulsars today are recognized as rotating neutron stars. They are giving off energy. They are rotating at anything from a few hertz to several thousand hertz, rotating several thousand times a second. So these are very significant events. Now, question. I know you've had nothing to do so far apart from listen. So a question for you. Estimate the mass of a teaspoonful of a neutron star. Take the density of a neutron star to be 1 × 10⁻17 kilograms per cubic meter, and size of your teaspoon about 2 cubic centimeters. So please now calculate the mass of a teaspoonful of a neutron star. Thinking, please, quickly about, as we've got 10 or 15 minutes and I've got 3 or 4 more slides to go through. So come on, please, let's see some answers. I can't see anything.
My chat doesn't work. Can I say my answer instead?
Of course.
I got 2 times 10 to the power 14.
Be careful, remember it's kilograms and it's cubic centimeters, 2 cubic centimeters. Daria, you are correct. Good. Thank you. I think your calculation would have been, let's firstly consider the contents of the spoon are 2 cubic centimeters. 1 cubic centimeter is 10 to the minus 6 cubic meters, not 10 to the minus 3. I think that's where the mistake probably came.
Yeah, I think so.
Yeah. So density is mass over volume. So mass is density times volume. 2 centimeters cubed is 0.000002, 2 times 10 to the minus 6. So the mass of a teaspoon of neutron star will be about 2 times 10 to the power 11 kilograms, which is about 2 billion tons. So you are looking at something which is going to give you indigestion, certainly if you tried to eat it. Thinking about it, if we were to try to walk on this star, that firstly it's very hot, so after it's cooled down, the gravitational forces would require you to have pneumatic legs the size of a skyscraper, and you would not be able to move on this environment. So the massive forces of gravity that are acting on here would be very, very limiting. So we've got the first objects which we can state and categorically understand are going to have some pretty intense forces acting on them. But things get even better, because one of the final reaches that we come to in the life cycle of our stars is that of a black hole. If the core remnant of a supernova, we're not now talking about the iron content at the core, but the remains of the supernova have a mass of greater than 3 solar masses, the neutrons are unable to overcome the gravitational forces. And what will then happen is the core will collapse on itself. And the core becomes so dense that not even light can escape from this core. What has happened now is that there is an object. We've talked circular motion. We talked about escape velocity in our circular motion and orbits discussion. So if now we get this object called the black hole, and the black hole now exists as a singularity. So we have an object which nothing can escape from. Its core is unknown because we just don't know what is inside there, what happens to these objects. Maybe there's a complete new branch of physics that we don't know about, that maybe is occurring at the center of this object called a black hole. Now we view these objects because in our greater scheme, we could have 2 stars, 2 supergiant stars that have been side by side. This star here had the relevant size to collapse to form a black hole. And this black hole we can't see, hence its name, a black hole. It doesn't exist on this stellar map. But what will happen is, if there are a pair of stars, so this is a supergiant next to the black hole, this star is going to have its matter attracted or accreted by the black hole. And that means the mass from this object will start to flow towards the black hole just here. And again, as we've talked in circular motion, these objects will spiral around each other. So the matter from the supergiant will spiral around and ultimately get to the black hole. By the time the matter gets to the black hole and crosses an event horizon that we'll look at in a couple of moments, that means they are traveling pretty quickly. And when an object is accelerating inside a gravitational field, we get the emission of X-rays. So we see evidence for this black hole, not by seeing the black hole, but by seeing X-rays seeming to come from nothing. And this is indeed what happened. The first black holes were found in 1971 when an X-ray source from what was called Cygnus, the star Cygnus, X being the depiction of X-rays, and 1 for it as the first star. So Cygnus X1 was the first observed X-ray source that was in the same location as a supergiant. And this showed us that the first star that was identified as a black hole was not seen as a black hole, but was seen as X-rays being emitted from something, that thing being the black hole. Now, we have completed the summary. So we've gone from, and I'll just put this all up for you and then describe it. Again, you'll see this in the presentation that you have. So it's sort of complete now up to the black hole. We've gone from the start where gases came together. If they started burning greater than 0.05 solar masses, they formed a protostar that went through these processes. Any star that didn't have sufficient mass just fizzled out and became a brown dwarf. So we go through the burning phases. We have the red giants down here. We have supergiants up here. We have planetary nebula, the result of a red giant dying. A supernova, result of a massive super red giant, resulting in the formation of white dwarfs, neutron stars, or ultimately here, the black hole. So this now is a complete evolution summary of all types of stars, of all events that we currently have as mainstream events. Now, of course, astrophysics and physics wouldn't be complete without exceptions. And there are exceptions, but they are just that, exceptions to the rules. These are part of what make up the evidence for the evolution of a majority of the stars that we can see. Now, one more slide, and then I'm going to give you a question for the rest of today. So we're going to just look at this event. When a black hole is formed, the distance from its center from which light can no longer escape has a very significant value. And this is known as what's called the Schwarzschild radius. It's defined, Schwarzschild radius 2gm/c². You may recognize this as part of the equation where we calculated the escape velocity. In this equation, as we know, we cannot travel faster than the speed of light. The speed of light is the limit to where we could find ourselves in this singularity. And the Schwarzschild radius can be defined as what we call the event horizon. And that is the boundary inside which you will never get out. So you've heard of processes spaghettification. where gravity stretches things and objects. Well, we get to the event horizon where spaghettification takes place, but everything seems to come to a stop because you've moved into that region where light cannot escape. So no longer can you observe what happens after you've crossed over that event. Question for you to do for the rest of the lesson and by the end of tomorrow, please. Calculate for a black hole of mass 3 times the sun its Schwarzschild radius, and then its mean density inside the event horizon. So 2 simple parts to the question. It's 2 or 3 lines of calculation, and please submit into the classroom. There is an event there for you, so please put your answers into the classroom. Any questions? You're going to see from today onwards, the materials that I've posted will start to achieve more solutions. So I will change some of the presentations for you, but I won't do it until after I've got the solutions to this question, please, submitted into the classroom. Right, so questions, is the video presentation due April 16th, correct? Yes. SPT comments, you will get those during the Easter break. That is something I'm trying to get into the school soft. So you will get those, and I'll put those all to all of you. What do you mean when you say the questions will have multiple solutions? Which questions are you talking about? Multiple choice. You have multiple choice questions, which are, as the suggestion is, there are 10 questions. Each question has 4 solutions. You have to choose the correct solution. The main part of the questions So the second part of your question paper, they are multiple part questions. So there is generally a description part followed by a calculation part. And you answer them however you can in the classroom. I mean, in the school classroom, not on the Google Classroom. Okay. Right, I've just finished taking the register, so hopefully all of you have now got your question. It's in the classroom, as you can see. Please try and get that done for me for tomorrow, and I will see you after the Easter break. So I wish you all a very pleasant break. Come back refreshed, get all your work done. You're 6 weeks away from graduation, so you're almost there. Okay? See you later. Bye for now.
Thank you.
Have a nice break.
Thank you. Have a nice day.
Bye.
Bye for now.
Mr. Richardson,
Yes.
just please don't forget me with the register, because my chat wasn't really working today.
I have you in. I've copied the comments as well, Charlie, so I can see all of the people.
Okay, perfect. Thank you. Goodbye.
Thanks a lot. Bye for now.
Bye.
Bye.